All right, now let's return to our analysis of variance table and see if we can bring ourselves back to the same decision relative to the hypothesis that a to a minus a to b is equal to 0. To do this, I have to set up another mathematical model. See, this mathematical model is inappropriate because I knew a good deal more about the data than it implied. And so I'm going to set up a second mathematical model. And the second mathematical model in this case is the following. The individual observations are equal to mean plus tau sub j. Now the tau sub j's are little fixed effects which the observations endure for being in one classification or another. The observations in classification A get a fixed effect, and we're going to call that tau sub a, I guess. Every one of them gets a little impact just for being in classification A. And all the observations which fall in classification B, they're going to get their own little impact for just being in classification B. And then, in addition, on top of everything else will be sprinkled, Mother Nature is going to sprinkle an error. And we're assuming that those errors are normally and independently distributed with mean 0 and variance sigma squared. Okay, let's see what the consequences in the analysis of variance table are of having this new model. Well, we'll have to estimate all the parameters, and I have already estimated the parameter eta with y, the grand average, and that continues to be the proper estimate. But now let's estimate the parameters tau a and tau b. And to do that, I want you to recall what the average for treatment A and the average for treatment B is. The average for treatment A was 6. The grand average, I beg your pardon, the average for treatment A was 9. The grand average was 6. All right, now if you had to guess, or you had to estimate what the impact on the observations for being in treatment A was, what would you suggest? The average for the A's is 9. The grand average is 6. And so you would come up, I would trust, right, with the idea that 3. Every observation in treatment A apparently is enhanced by 3 units. That would be your predicted value for the treatment effect. And pray, what would be your predicted value for the treatment effect of the observations in classification B? R, you say. Let's see. The average in B was, the average of all those B's was 4. And the grand average is 6. So I get the impression everything's knocked down by 2 in treatment B. And so I would estimate the effect in treatment B to be minus 2. Okay, gang, now you'll see me actually placing those individual estimated effects along with each observation. The first 4 observations pick up a plus 3 because they were in classification A, and the last 6 observations pick up a minus 2 because they were in the second classification. And now, how about making this mathematical model work? What about that equal sign? It says every observation can be explained away in terms of the mean, which is estimated by the grand average, and the effect, which we have estimated here. And to get that equal sign to work up, I'll have to calculate some residuals. And I have the table of residuals here. And you will notice that 8 is equal to 6 plus 3, and then the residual minus 1. And so it is all the way down the line. Now, just as previously in the analysis of variance table, we worried about the sum of squares column. Let's return to the sum of squares column and grind out the sums of squares of these particular effects. If you take the sum of squares of these little estimated treatment effects, it'd be 9 4 times and 4 6 times, and sum them up, you'll find out the sum of squares for the treatment effects will turn out to be 60. And if you take the sum of squares of the residuals, the things that are left over, take those sums of squares, do you know what it comes out to be equal to? By golly, it comes out to be equal to 42. And that's very interesting because earlier, when I had the earlier model, which I've now dismissed, I had a total sum of squares of residuals of 102. And you'll note that I take what's happened in this instance, that this residual, the earlier residual sum of squares, has now been partitioned into 2 sources, one of which we can blame on the treatment classifications, if you will, perhaps the difference between the 2 treatment means, if it's there, and the remainder due to intrinsic variability that we don't have any ready explanation for. Now, what about this degrees of freedom column? Well, we still have 10 degrees of freedom for the observations. Calculating that statistic cost me a degree of freedom. How many degrees of freedom were used to compute these statistics minus 2 and the statistic 3? And the answer is not 2, I'm sorry. You know, those things happen occasionally, right? The answer is 1. And the reason why the answer is 1 is the following, that this line, or this set of data here, are constrained. All those effects have to sum to 0. And I'll tell you, gang, the minute I knew that the treatment effect for treatment 1 was equal to 3, I could have predicted in advance that this would have been minus 2, because I'd have to arrange things so the entire sum here comes out to be 0. These are algebraic constraints which are built into the analysis of variance table. And so we say, as a consequence, that we've only consumed, if you will, 1 degree of freedom in estimating the treatment effects. And so let's put it down there. And by golly, how many degrees of freedom does that leave over for the residual? Well, I've consumed 2, so how many degrees of freedom are in the residual? Well, 8 degrees of freedom are in the residual. Now, just as I did the last time, let's estimate the variance by taking the sum of squares for the residual, for the last line in the analysis of variance table, and divide it down by its degrees of freedom, all right? And so if I do, I'll get a second estimate of the variance, and I wish I could find it here. The second estimate of the variance in this case is going to be 42 divided down by 8. 42 divided down by 8 is a familiar statistic. You've already seen that. And if we return to the board, you'll see it there in all its clear glory. The estimate of the pooled variance, the pooled estimate of the variance is 42 divided down by 8. And you will note that on that analysis of variance table, the residual sum of squares came out equal to 42, and the number of degrees of freedom in that associated with that sum of squares was equal to 8. And so we can manufacture, using the analysis of variance table, an estimate of the variance with 8 degrees of freedom, getting the same estimate as we got here earlier. But what about this problem of testing the hypothesis and so forth? We have that to fight. But before we get back to actually seeing the machine we were going to construct the analysis of variance table for testing that hypothesis, let me show you a way for sort of speeding up the calculation of the sums of squares which enter into the analysis of variance table. The one particular calculation I can speed up is the calculation of the treatment sum of squares. And let me show you the alternative and algebraically equal set of formulae which I can use for getting that sum of squares. If you want to get the treatment sum of squares somewhat more quickly, here's one way you can do it. You can take the total for treatment A, square it and divide by the number of observations in treatment A. Take the total for treatment B, square it and divide by the number of observations in treatment B, and subtract out the correction factor. Now you should remember the correction factor is the grand total squared divided down by the total number of observations. Okay? Now let's actually see that calculation. Let's see the substitutions. Well, the total for A was 36 and the total for B was 24. Square that and divide by 4, so on. The grand total was 60. And you'll find that the treatment sum of squares, upon completing that calculation, the treatment sum of squares was equal to 60. And so it's possible for us to get this entry in the sums of squares column, right, in a manner separate from the one we initially indicated, in which we actually computed out those individual estimated treatment effects. Now, most analyses of variance table do not have all these deviations spelled out, and so what I'm going to do, I'm going to try to collapse this table a little bit. The first line in the analysis of variance table is usually called the crude sum of squares line. The second line, that 360 is, of course, as you know, the correction factor, and so let's just call it the correction factor line. The third line is sometimes called the treatment sum of squares line, and the fourth line could be more briefly termed the residual sums of squares line. And if you liked, we might even identify these things symbolically. We could talk about the various sources of variability which enter into the data. First of all, there's the grand sum of squares of all the observations, the intrinsic quantity which we begin to work with. Then there's the correction factor, and then there's the treatment sum of squares, and then there's the residual sum of squares. And this would permit us to tighten up our table a great deal. In that fashion, that would be the sum of squares column right there. And then we'd have the degrees of freedom. This is always equal to the total number of observations. This always costs us 1. We will find later that when we generalize the use of the analysis of variance table, that doesn't have to be 1. There may be k treatments compared, and if that were the case, we'd have k minus 1 degrees of freedom. And of course, this is always the residual, whatever is left over. So really, our analysis of variance table, the ones you usually see published, would be generally limited between these three columns you see right here. All right. Now, what I want to do is proceed and see if I can get you around to that test of significance. Now, as I commented earlier, if you take the residual sum of squares and divide down by its degrees of freedom, you'll get something, you'll get the estimate of the variance. And that's sometimes called the mean square. So the mean square in this case is 5.25, and you'll remember that the mean square, 5.25, is our estimate of the variance in the second situation. All right, now let's set up the hypothesis, a to a minus a to b is equal to 0. That's identical to setting up the hypothesis that tau a and tau b are both equal. Now you remember our earlier model didn't have the taus in it. So if I hypothesize that the taus are 0, I really return to the earlier model. And the earlier model had for the sum of squares of residuals 102 with 9 degrees of freedom. And so what we've done in this case is taken that 102 and divvy it up into 2 portions, and we've taken the 9 degrees of freedom and divided it up into 2 portions as well. And in this instance, the 42 divided down by 8 is certainly still an estimate of the variance, but what about the other term we see down here? Suppose I take this degree of freedom, which under the hypothesis that nothing is going on is also an error degree of freedom now, and divide it into the 60. If I were to do that, I'd get a second mean squared equal to 60. And this second mean squared is every bit as good an estimate of the variance as the first. In point of fact, we talk about the expected values of the mean squares. The expected value of that mean square continues to be sigma squared. It's based off the residuals. But this quantity here also estimates sigma squared given that the tau j's are all equal to 0. So it's constrained by the hypothesis. Well, now we have 2 estimates of the variance. What we do in this case, we work up a statistic called the F statistic. The F statistic in this case will have 1 and 8 degrees of freedom. It's equal to 11.43. The F statistic was created by a very famous statistician by the name of Sir Ronald Fisher. Sir Ronald Fisher was a genius, a man of many parts. He did some work in mathematics. He did his original work in mathematics. He became very much interested in genetics. And he once told me when I was a student and I had an opportunity to meet him, he once told me that he got interested in statistics because he had to get the important problems in genetics out of the way, and statistics was sort of getting in his way. It wasn't properly thought through, and so he spent his energies, much of his energies, straightening out statistics. He is, I guess, the most famous of all the statisticians, responsible for the analysis of variance table and for a multiplicity of other important ideas. Let's look at the F distribution, which he created. The F distribution is a 2-parameter distribution, as you see here. And you have to have 2 parameters, and here are a multiplicity of F distributions. You'll notice they're badly skewed distributions. In our case, we have a F statistic, F with 1 and 8 degrees of freedom equal to 11.43, and the critical value, and the critical question is that an important or rare event, rare value for F? And I can quickly determine that by looking that up in a set of tables too. And it turns out the critical value of F with 1 and 8 degrees of freedom is 5.32. That's the value of F that leaves 5% in the tail of the curve. And so this is, in fact, a rare event. And it would lead us to reject the hypothesis that the taus are all equal to 0. That's the same hypothesis we just tested a few moments ago. And you will notice that in testing that hypothesis, we used the F distribution. You will find out in practice that F, when it has 1 degree of freedom in the numerator mean square, is equal to t squared. For those of you who are good at multiplication, you might want to square up 3.38, our observed value of t. You'll note that it gives us the observed value of F. Okay, gang. Well, I think that just about completes our investigation of the data in this particular instance. I'll tell you one trick you should always pull when you do an investigation is that you should completely eliminate all the information which was residual in the data. And if, contrary-wise, you should ever be a criminal, you'd be wise to completely eliminate all the information as well. We'll be seeing you.